This is session C2, Schrodinger Equation and Energy Eigenvalues. Last time we did wave mechanics of matter waves. We used the free particle in one dimension to develop the Schrodinger equation. Today we're going to explore the Schrodinger equation generally. We will learn about energy eigenvalues and energy eigenfunctions. In the last lecture, we used a specific problem, a free particle, an unbound state, to develop the Schrodinger equation. Starting with the next lecture, C3, we will use a different specific problem, particle in a box, to learn how to use the Schrodinger equation and learn about quantum mechanics for bound states. In this current lecture, C2, we will not solve a specific problem. We'll look at the Schrodinger equation generally. Generalities and abstractions in this lecture will become concrete starting with the next lecture. If this lecture becomes too daunting, either because there's too much new material or because it's confusing to think about both spatial wave functions and spin problems, get what you can out of this lecture and proceed to the next lecture. You don't have to memorize anything from this lecture. When we need some material in further lectures, I'll present it again. Here's the time-dependent Schrodinger equation. We use the acronym TDSE, which is non-relativistic. We learned this in the last lecture. IH bar partial of psi with respect to t, time, equals the Hamiltonian operator times Hamiltonian operator operating on the wave function psi, capital psi, where h hat is the Hamiltonian operator for the specific particles and system we want to solve in a specific problem. The Hamiltonian operator, also known as Hamiltonian, has dimensions of energy. In the last lecture, we saw the specific Hamiltonian operator for a free particle in one dimension. Here we want to stay general and not write a specific Hamiltonian for a specific problem. Capital psi is a or some time-dependent wave function solution of this Schrodinger equation for this particular Hamiltonian, so specific to a specific problem. Psi has dimensions, as we'll see in a future lecture, but we don't need those dimensions today. H bar is the reduced Planck's constant with the dimensions of energy times time, and I is the imaginary unit. This is a possible time to take a break. The Schrodinger equation is linear in psi, as psi appears on both sides of the equation. For the time-dependent Schrodinger equation with a given Hamiltonian, if psi is a solution, then so is alpha times psi for any complex number alpha. If psi sub 1 and psi sub 2 are solutions, then so is any linear combination alpha times psi sub 1 plus beta times psi sub 2 for any complex numbers alpha and beta. Therefore, a solution is not unique. A given wave function psi is not a unique solution. In the last lecture, we found the wave function, the Schrodinger equation, and the Hamiltonian for a free particle in one dimension. In that problem, the Hamiltonian was spatial. It included the second partial derivative with respect to x. The wave function was a continuous function of position x. It also included momentum p. Many problems that we want to solve with quantum mechanics are spatial. For example, for the hydrogen atom, we have a known potential energy function for the electron's position relative to the nucleus, and we have a kinetic energy operator, so we have a Hamiltonian operator for this system, and we want to find the allowed energies for the system, and we want to find the probable locations for the electron, the atomic orbitals for the atom. However, there are other important problems that we want to solve with quantum mechanics that are not spatial. Subatomic and elementary particles, such as the electron, proton, neutron, and photon, possess an internal, intrinsic degree of freedom, or property or attribute, independent of its motion. The name for this property is intrinsic spin angular momentum, or spin. A little bit of angular momentum that is intrinsic to the particle and independent of the particle's position or motion. I don't want to explain here what angular momentum and intrinsic spin angular momentum are and how they show themselves or are measured. We'll cover that in the D series of lectures. Spin really is angular momentum, but the particle is not spinning. Spin also makes the electrically charged electron a little magnet, a magnetic dipole. Ferromagnetic materials, iron and nickel, get their magnetism from the electron's spin and magnetic moment. If you have learned about atomic orbitals in chemistry, you've probably heard of the electron spin and the m sub s quantum number. Angular momentum and spin are very interesting and important and mysterious, and we will look at spin in the D series of lectures. Non-spatial quantum mechanics problems with an internal intrinsic degree of freedom, such as spin, can also be solved with the time-dependent Schrodinger equation. In these cases, solutions are abstract wave vectors instead of wave functions. A wave vector can be represented as an n-dimensional abstract vector of complex values, which may be continuous functions of time. The spin of an electron, or a proton, or a neutron can be represented as a two-component complex valued vector whose components may be continuous functions of time. And we can write this two-component vector as a top component and a bottom component, where here the top component is alpha of t, which is a complex function, and the bottom component is beta of t, a complex function. This is a spin state. It is not a vector in position or coordinate space. It does not point in a two-dimensional spatial plane. The Hamiltonian operator, or Hamiltonian, is a Hermitian n by n square matrix of complex values which may be continuous functions of time. I will not explain what Hermitian means in this lecture, but it imposes constraints on the components of the n by n matrix. The spatial Hamiltonian operator is also Hermitian, but I will not explain this here. The Hamiltonian for the spin of an electron, or a proton, or a neutron, can be represented as a 2 by 2 matrix whose complex valued components may be continuous functions of time. This is a possible time to take a break. The wave function or wave vector represents a complex valued probability amplitude, which is not directly measurable. Both types of problems, spatial and spin, can produce wave interference, constructive interference, or destructive interference. The time-varying wave function or wave vector, capital psi of t, is almost always complex valued. For the probability amplitude, we can derive a probability density for a spatial problem or a probability for an intrinsic degree of freedom problem, such as a spin problem. And these are measurable with suitable measurements. For a spatial problem in one dimension, where the particle is in a bound state, not a free particle, the probability density rho of x and t is the complex conjugate of psi times psi divided by an integral over all space, which means all x, of complex conjugate of psi times psi. We will get experience with this in coming lectures. Probability measurements are taken for a large ensemble of identical systems in identical states, identically prepared as much as possible. Doing a measurement can alter the state of a system, so we cannot generally keep remeasuring a single system to learn everything about its probabilities. We need an ensemble of identical systems to measure. It's confusing that we cannot keep measuring a single system, for example, a single atom, to learn everything we want. Probabilities apply to large ensembles of identically prepared systems. Nevertheless, we talk about the probability density for a single system or the probability for a single system, but we mean it to be measurements of ensembles of identical systems. The Hamiltonian for a system we want to solve may have an explicit dependence on time. For example, there may be a time-varying external electric or magnetic field, or an electromagnetic wave. The particle may be moving in space where an external electric or magnetic field varies in space. Or there may be some size constraint on the system that we are varying in time. The Hamiltonian will never have a time derivative that operates on the wave function, however. We can rearrange the time-dependent Schrodinger equation so that the left side only has a partial derivative with respect to time. Partial derivative of psi with respect to time equals 1 over IH bar H hat operating on psi. The time derivative of the wave function equals the expression on the right-hand side. For a spatial problem, if we know the Hamiltonian at all times and we know the value for the wave function at all points in space for some specific time, call it t equals 0, then we can integrate this equation to give the wave function at all points in space and all times. This can be complicated if the Hamiltonian depends explicitly on time, but can always be solved by numerical integration on a computer. This is a possible time to take a break. Now we'll look at the time-independent Schrodinger equation. when the Hamiltonian for a system that we want to solve is not explicitly dependent on time. So for a spatial problem, when the potential energy function is not explicitly dependent on time. Then the time dependence of the wave function is greatly simplified, and finding solutions is easier than for time-dependent Hamiltonians or potentials. Certain very important time-dependent wave functions can be found that are the product of a time-independent function and a time-dependent, spatially independent function. These solutions will be of great interest. For a spatial problem in one dimension, there will be some separable solutions where capital psi of x and t equals the product of a spatial wave function, lowercase psi of x, times a function of time alone. We generally will use capital psi when we're talking about a wave function with its time dependence, and we will use lowercase psi for the wave function without its time dependence. So at fixed time, t equals 0. Note that f of t is independent of position. We can work from the time-dependent Schrodinger equation to derive the time-independent Schrodinger equation. I'm not going to derive it. It's not difficult. It's in books. I'm just not going to use your time to do that. I'll just give you the time-independent Schrodinger equation, or TISE. Hamiltonian operator, H hat, operating on time-independent wave function, lowercase psi, equals E times psi, where E is, we will see, is an energy. Since there will be multiple energies, multiple allowed energies, and multiple allowed wave functions, we'll write this instead as Hamiltonian operating on a particular wave function, lowercase psi sub n, equals energy E sub n times psi sub n, where E sub n is one of the real valued energy eigenvalues that solve this particular Hamiltonian for this system, and lowercase psi sub n, which starting now I will just call psi sub n, you can see that it's lowercase, is one of the energy eigenfunctions or eigenvectors that, with energy eigenvalue E sub n, solves this particular Hamiltonian for this system. We say that the state is an energy eigenstate. This will be very confusing at this point, and that is normal and okay. We will get concrete experience with this starting in the next lecture, C3. But for now, I still want to keep this general and abstract. So bear with me. Eigen is a German prefix meaning own, O-W-N, or self. The energy eigenvalues belong to the specific Hamiltonian we're solving. Remember, in any given problem, h will be specified for that problem. So energy eigenvalue E sub n will be one of the energies that solves this equation. So the energy eigenvalues belong to the specific Hamiltonian we're solving. These are this Hamiltonian's own energy values. And the wave functions corresponding to those energies we call Eigen Functions or eigenvectors. This is a possible time to take a break. The problem we are solving could be spatial or a spin problem. For a spatial problem in one dimension, we would write psi sub n of x. For a spatial problem, the potential energy function is real valued, and we can generally work with real valued spatial wave functions, psi sub n of x, y, and z. For spin problems, we must use complex valued wave vector representations. We will see this in the D series of lectures. We will get experience with energy eigenvalues and energy eigenfunctions beginning with the next lecture, C3, for the particle in a box. So don't give up with this lecture being abstract. Now, psi equals 0 is a trivial mathematical solution to the time-independent Schrodinger equation. Psi appears on both sides, so 0 equals 0 is a valid equation. But psi equals 0 is not a physical wave function. The probability is 0, and it does not represent the wave function of a particle state. So we will never see it again. We will not use it. This is a possible time to take a break. For energy eigenvalue E sub n and energy eigenfunction or eigenvector psi sub n, the time-dependent wave function or wave vector is capital psi of x and t equals lowercase psi of x, the spatial part, times the complex exponential e to the minus I e sub n t over h bar for a spatial problem in one dimension. Or for a spin problem, we don't have x, so capital psi of t equals psi times the complex exponential. Let's check this with the time-dependent Schrodinger equation. We'll just plug in. Time-dependent Schrodinger equation, IH bar, partial with respect to t of psi. We will substitute for psi. So we keep the IH bar, and when we take a derivative of a partial derivative with respect to time of this product, lowercase psi of x does not have any time dependence, and so it comes out of the partial derivative, and we're only taking a partial derivative of the complex exponential. So we get lowercase psi of x, and then the derivative of the complex exponential, the partial derivative with respect to time. Well, we know how to take the partial derivative of an exponential. We saw that in last video. So we keep the complex exponential, but we include a factor of minus I e sub n over h bar. Now, psi sub x and times the complex exponential, we can substitute back that is just capital psi of x and t. And we can cancel the h bars, and I times minus I is plus 1, so we get e sub n times capital psi. And from the time-independent Schrodinger equation, we know that h psi equals e psi. So we can get back h bar operating on psi. I should have rearranged these steps. It's e sub n times lowercase psi that gives h operating on lowercase psi. And h is not time dependent, so it does not operate on the complex exponential. Note that the time-independent and time-dependent wave functions are identical at the special time t equals 0. At t equals 0, the complex exponential becomes e to the 0 or 1. So capital psi of x at t equals 0 equals lowercase psi at x. This is a possible time to take a break. For energy eigenfunctions, eigenvectors, the probability density or probability is independent of time. The energy eigenstate is a stationary state because the complex phase cancels when we take psi star psi. Let's see that. Psi star psi. So we need to take the complex conjugate of psi, and this is psi, times psi. Well, when we take the complex conjugate of a product, that is equal to the product of the complex conjugates. So we get psi star, and the complex conjugate of a complex exponential just negates the exponent. So we turn minus I e sub n t over h bar to plus I e sub n t over h bar. And we can rearrange this product of 4 terms. We can move this psi to the left. So we get psi star psi e to the plus I e t over h bar e to the minus I e t over h bar. Well, the product of these two complex exponentials is 1. So we get that capital psi star capital psi equals lowercase psi independent of time for an energy eigenstate, which is special. The time dependence has canceled out here. This is a possible time to take a break. A system might be in an energy eigenstate with a single definite energy and eigenvalue, but the system could generally be in some superposition state, any linear combination of multiple energy eigenstates. Let's look at a simple case of a spatial system in 1 dimension whose state is the following superposition or linear combination at time t equals 0. Capital psi of x and time equals 0 equals c sub 1 psi sub 1 of x plus c sub 2 psi sub 2 of x, where psi sub 1 and psi sub 2 are energy eigenfunctions of this Hamiltonian corresponding to energy eigenvalues, E sub 1 and E sub 2, and C sub 1 and C sub 2 are complex numbers. It turns out we can immediately write out the time-dependent wave function for any time t for this superposition of energy eigenstates, which makes it very useful. Capital Psi of x and t equals C sub 1 psi sub 1 of x times this complex exponential with energy E sub 1 plus C sub 2 psi sub 2 of x times this complex exponential with energy E sub 2. This is very convenient. So we knew psi of x at times t equals 0. We knew it at all positions in space. And now we know it at all positions in space and time. And we didn't have to integrate, and we didn't need to do a numerical integration on a computer. The fact that we could express psi in terms of energy eigenfunctions allowed us this very simple way of knowing what the time evolution of the wave function is. Beware, the probability density for this superposition state, or any superposition state, is not independent of time. This is not a stationary eigenstate. You can verify this by taking capital Psi star times capital Psi for this superposition. We won't do this here, but we will examine this in a future lecture. Now it happens that every solution to the time-dependent Schrodinger equation for a given Hamiltonian that is not explicitly dependent on time can be written as a linear combination of the system's energy eigenfunctions from the time-independent Schrodinger equation with their complex exponential time-dependent phase factors. We will not prove this. Solving the time-independent Schrodinger equation gets us close to the solutions for the time-dependent Schrodinger equation. The general strategy for solving problems in non-relativistic quantum mechanics with the Schrodinger equation is to first solve the time-independent Schrodinger equation when we can, to find the energy eigenvalues and energy eigenfunctions, eigenvectors, and then apply the correct time dependence or time evolution to the required superposition states. This is a possible time to take a break. For a spatial problem for a single particle, when there is no magnetic field or the magnetic field can be neglected, the Hamiltonian is h hat of xyz in time equals minus h bar squared over 2m del squared. This is the kinetic energy term, the kinetic energy operator, non-relativistic, plus v of xyz and t, where v of xyz and t is the real valued potential energy that the particle experiences. An operator del squared is the sum of second partial derivative with respect to x plus the second partial derivative with respect to y plus the second partial derivative with respect to z in Cartesian coordinates. Del squared can also be used in cylindrical coordinates or spherical coordinates we won't give those formulas here. Quantum mechanics can solve problems with more than one particle, but it gets complicated and we won't do any multi-particle problems. This is a possible time to take a break. Now let's compare spatial quantum mechanical problems versus spin problems. The second column will be spatial problems or momentum problems. The third column will be problems with an internal degree of freedom, which is generally spin. The Hamiltonian operator for spatial problems is the appropriate total energy operator, which will be Hermitian, which I'm not going to explain, including kinetic energy operator, second partial derivatives with respect to position, and potential energy, which may depend on position and may depend on time. For a spin problem, the Hamiltonian operator is an n by n square matrix, which will be Hermitian, of complex values, which may be continuous functions of time. For electron spin, that will be a 2 by 2 matrix. The wave function for a spatial problem will be a continuous function of position and time. For a spin problem, the wave function, we will call a wave vector, will be an n-dimensional abstract vector of complex values, which may be continuous functions of time. For electrons spin, that will be a 2-component complex valued vector. This is an abstract vector, not a vector in space. Now, what terms will we use for the wave function? For a spatial problem, we will generally call it the wave function. We may call it the state. Less often, we might call it a state vector or an electronic state. For spin problems, we will call it a wave vector instead of wave function. We might call it a state vector, a state, or a spin state. Now, when the wave function is an eigenfunction, for a spatial problem, we'll call it an eigenfunction or an eigenstate. For a spin problem, we will call it an eigenvector or an eigenstate. We can use many different symbols for wave functions. For a spatial problem, we will generally use capital Psi when we're including time dependence, and we'll generally use lowercase psi when we're looking at the time independent portion. We will generally psi will have an index, a subscript. We will generally use n when the index is an integer, which is generally for bound states. And we will generally use k, a real number k, the wave number, for unbound states such as a free particle, where the energy is continuous, not discrete. Now, for some problems, we will need more than one index. You might know that for the hydrogen atom, for the wave function for the electron in a hydrogen atom, we will use three indices, n, l, and m, each integers. Sometimes we will express a wave function not in terms of position but in terms of momentum. And when we do that, it's more normal to use capital phi or lowercase phi for the wave function instead of psi. Now for spin wave vectors, we can use capital psi, but you will also see lowercase chi, or you will, for electrons, you may just see the vector showing both components, a top component, which I'm calling alpha, and a bottom component, which I'm calling beta. This is a possible time to take a break. Now there are some other symbols, and we will use them. I'll explain them more later, but they are called kets, or ket symbols. A ket is a vertical bar, a label, and then a right angle bracket. The combination is called a ket. Ket comes from the last half of the word bracket. The ket symbol allows us a lot of flexibility in terms of what we put for the label, which is why we use it. We can just put in the symbol for the wave function. So this is the ket psi, or lowercase psi, or phi. But with the ket, we have more flexibility. So we might call one wave function u and another wave function v, or we might use n to show that we know that the wave function is for some integer value n, and we can plug in that integer value when we need it. So if we plug in 0, we get the ket, the 0 ket, or the 1 ket. We also can plug in a position or a momentum in the ket. This will be confusing. We will use this later. I'll explain it as we use it. For spin states, we can put psi in the ket or chi in the ket, or we can label two different spin states, u and v. But we will see later that spin states also have a directionality relative to real directions in space, x, y, z. The spin state vector is not a vector in x, y, and z, but we'll see that it is related to directions. We'll see this in the D series of lectures. So we will see a ket z plus and a ket z minus, where z is the z-axis. We will also see a ket of plus and minus, or up and down, or x plus and x minus. Now we also have symbols for energy eigenvalues. We always use E, capital E, for energy, but we can have a subscript n, an integer subscript, for discrete energy levels, or a subscript k for continuous energy levels, or we can have multiple subscripts. For the energy levels of an electron in a hydrogen atom, we have two integer subscripts, and an L. For spin energy eigenvalues, we could use E or E sub 1 and E sub 2. There will be two energy eigenvalues for electron spin. Or we can use E plus and E minus to mean the more positive energy eigenvalue and the more negative energy eigenvalue of the two. Probability is confusing. We will get more experience with it in coming lectures. For spatial states, a state has a probability density function, a probability per unit length, area, or volume, depending on whether it's one-dimensional problem, two-dimensional, or three-dimensional. Probability of being near a given point in space, alternatively near a given momentum. For spin states, the state has a probability, not a probability density. A number, such as 1 or 1/2. A real number in the range 0 to 1. Now, this lecture has been very abstract and general, and some of this will have been confusing, and we will address that by getting more concrete in coming lectures. But I believe that there's value in seeing the generality not just once, but multiple times. I recommend that you repeat this lecture after you complete the C series of lectures, which will be on particle in a box, a spatial problem, and then again after you complete the D series of lectures, which will be on spin states. This is the end of session C2.